So in this class, we will today talk about the concept of hybridization. So what do you mean by hybridization? The word hybrid means it is a mixing of pure substance. So in the case of forming molecular orbitals or for bonding, let us first discuss about a very simple molecule, methane. So methane has CH4, so carbon has 4 hydrogens. Now this carbon will be called as central atom. The central atom carbon has 4 bonds. That means this is actually called a tetravalent atom. So this is the most stable system when the carbon is in tetravalent state. Now let us see the electronic configuration of carbon atom. It is 1s2 2s2 2p2. Now important thing is that whenever you call about electronic configuration, you have to consider it in the ground state. So accordingly it is written in this way that carbon, sometimes it is a ground state or sometimes it is written as GS. So carbon in ground state have electronic configuration 1s2 2s2 2p2. This is how you can represent an electronic configuration within an orbital. So this is 1s, this is 2s, this is 2p. Now, so according to this electronic configuration, if I am asked you to uh, talk about the valency of the carbon, then you can say that because it has 2 unpaired electron, it might have a valency of 2, so carbon should be divalent. There are very few examples of divalent carbon atoms, like for example carbene, which is called CH2, which is called carbene. This is an intermediate in organic reactions, but these are very much unstable and very rarely found. So but in most of the case we find a tetravalent carbon atom, and these are the most stable carbon in the nature. Then there is definitely something happening through which the carbon is going from the divalent state to the tetravalent state. That means it has to contain not 2 but 4 unpaired electrons. These are paired electron and this is unpaired electron. Okay, and then only it can form 4 such bonds. So what is possibility here? Now the most stable is tetravalent valency 4. How is it possible? It is said that the carbon atom must be energetically raised to its valence state. Then only this electron pair can be unpaired. So what is this and how is it possible? That means there must be some promotion of the electron from 2s to the 2p, and this promotion of one 2s electron to vacant 2p orbital, this is vacant, there is no electron, so this is vacant. So this is possible as it is reflected here. Carbon ground state 1s2 2s2 2p2, and carbon in the valence state is 1s2 as it is, and in this valence shell, that is, what is valence shell? There is the last in the atomic electrons which is in the last orbital, that is 2s2 orbital. So 2 subshell. So here C valence will be 1s2, and from 2s one electron has been transferred to the vacant 2p orbital. So now you have 1s2, 2s1 and 2p3. That is, there are now clearly 4 unpaired electrons. Now they are capable of forming 4 such sigma bonds. Basically these bonds, what is these bonds? This bond require 2 electron. One is coming from carbon and one is coming from hydrogen. They form a covalent bond. So now just if you realize, if there are one electron in any orbital, suppose is one of the orbital of the carbon, so it can attach with one of the electron of the hydrogen. Likewise in there are 3 such things. So this is how now, as the carbon through this promotion is excited to the valence shell or valence state or excited state, now they are able to form a tetravalent carbon which is capable of forming 4 such bonds. Now, so we can define the valence state as the state of an atom in a molecule without any bonded atom. That means this is an valence state or excited state of a molecule or of an atom in a molecule where still no such bonds are formed like we have seen here. This is we will come later when we talk about entry into the when we enter into the hybridization concept. Until now we have this, we have created the, or we have promoted the carbon ground state electron to its excited level, that is called valence state, and this is the valence state or excited state electronic configuration of carbon. So next comes how then this methane molecule forms. Here you have to enter in a new concept that is called, what we are intended to talk about here, that is called hybridization. Let's see how does it work. Now in nature or in anywhere, what do you mean by the concept of hybridization? Hybridization is nothing but mixing. Whenever you have, suppose, two pure substances, and if they have different properties, they can be mixed and form a hybrid system so that you can get properties of both in a mixing way. That is, if you have, suppose, A and B, these are all pure substances. Now you mix them and have a system of AB. This mixing of pure A and pure B to form a coupled kind of system is called, is a method of hybridization kind of thing. This is a very general concept. We'll talk in detail about the orbitals, and this system will be called hybrid system. Now this hybrid system will not represent the property of individual A or individual B. Rather, there will be a mixing of the properties, and you can make it some percent of the property of A and some percent of property of B, and depending on various things, it has different type of properties or characteristics. Now let us implement this concept of mixing or hybridization in case of orbitals. Remember, we had talked about carbon atom, and we have made a promotion of electrons from carbon ground state to the carbon excited state. What it was there? It was a kind of carbon in valence state, that is 1s, 2, 2s, sorry, 2s, and 2p. Now, according to the concept of hybridization in orbitals or electronic configuration case, we say that the hybridization consists of mixing or linear combination of pure atomic orbitals to form a new set of hybrid orbitals. Again I say that hybridization consists of mixing or linear combination of pure atomic orbitals, that is here 2s and 2p, these are pure orbitals, to form a set of new hybrid orbitals. Now implement these things. You have, so 1s2 electron has not changed anything from the ground state to the valence state, so you don't need to think about it. Through the promotion of electron, what happened? One of the 2s electron went to one of the vacant 2p orbital. So through this hybridization, this 2s and 2p are going to mix. So how many orbitals are there in case of 2s? It is 1. And how many orbitals in case of 2p? That is 1, 2, 3. These are termed as px, py, pz. This x, y, z are nothing but the according to the axis. It is not that you have to say this first one as px. It is not that. You can name the first one pz, py, px, etc. This is nothing. This is only because of such axial orientation. If you call x, y, z, this px orbital will be like this, py will be like this, and pz will be like this. And s has no directions. It will have, it is spherical, symmetrical. So these two orbital, that is 2s and 2p x, 2p y, 2p z, they start to mix with each other. And what will be the result? The result will be a complete new set of 4 orbitals, and this follow the rules of linear combination, that is number of, this is very important, number of pure atomic orbitals. Atomic orbitals, you can write AO will be is equal to number of hybrid orbitals. Here, how many orbitals are there? 1, 2, 3, 4. So this will result, if you mix these things, it will result a new set of 4 hybrid orbitals. Now two things arises. What will be the shape of this new hybrid orbitals, because this will no longer be purely spherical or purely dumbbell shape like the pure p orbitals. So what will be the, how does it look like, and what will be the angle between these 4 orbitals, or the geometry, as I say. And this is very important because that geometry will give these hybrid orbitals and the resultant molecules as a specific geometrical shape. Now first thing we must say that, as here we are mixing one s and 3 such p orbitals, px, py, pz, this new set of orbitals will be called sp3 hybridization. So we can make a small table. This is hybrid orbital sp3. That means you have 1s3p. If the s can mix with 2p orbit, that is 2s1 with only 2, without this one, this does not participate. So in case of that will be called sp2. That means 1s a 2p orbital, 1s 2p. And if another mode of hybridization is sp, that is 1s and 1p. I will talk about the detail of this sp2 and sp orbitals. So let us first concentrate on sp3 as we are talking about these things. So how does it look like? So through this combination, it is observed that the resultant hybrid 4 hybrid orbitals, which is result of a mixing of 1s and 3p, that is 4 sp3 hybrid orbitals, will look like the 4 lobes of hybrid orbitals will be projected toward the corner of a tetrahedron, resulting in a geometrical tetrahedral shape, and it will look like this. Considering this, it is difficult to draw a tetrahedron because it is a two-dimensional board. I can show you in a 3D how to draw it, but it was observed that through this combination of S and 3p, you will get an sp3 hybridized carbon, around which these 4 hybrid orbitals will be projected towards the corner of the tetrahedron in such a way that the bond angle between any of these 2 orbitals will be 109 degree 28 minutes. This is a typical bond angle of a tetrahedral molecules. The perfect example of that is what you are observing here in methane, where you have an sp3 carbon which is tetrahedral in shape, this methane molecule, and this carbon is sp3 hybridized. That means it has a mixing of S and 3p, thereby it will for sp3 hybridization. Now with this 4 hybrid orbitals of the carbon, 4 hydrogen atoms will come with this 1 electron. And remember one thing, carbon has 4 sp3, carbon has 4 sp3, and 4 hydrogen will supply 1s orbital. That will result in a methane molecule, which by bond line representation you can find it here, by orbital representation you can find it here. And now this bond angle, that is H C H, these are all H H is HCH bond angle will be 109 degree 28 minutes, and this is a tetrahedral molecules. And you can, through orbital representation, you can represent a tetrahedral molecule in such a way. In a orbital box diagram, you can represent it first carbon atom in ground state, then carbon atom in valence state. You make some hybrid. So from this one you can now attach 4 hydrogen atom. So you will get a CH4 molecule. So this is how you can represent a sp3 hybridized molecule, and this is the representation of hybrid system or hybridization. So one thing you must consider, that if someone asks you why methane is tetrahedral, the common thing is, often the student says that because it is sp3, so it is tetrahedral. But this is not the case. Remember one thing, this methane is tetrahedral because it finds the maximum stability in such geometry. Now the attainment of such geometry is possible through this sp3 hybridization of the central carbon. So it is not the primary importance. The important thing is the stability of the methane molecule in the tetrahedral geometry, and that is possible to attain through the sp3 hybridization of the central carbon atom, and that is why methane is tetrahedral. So don't make a mess of it, because hybridization is not the reason. It has to be there in such a way that the molecules get a maximum stability in that geometry. This is very much important. Now we'll shift our system to sp2, and then we'll go to sp. Now what happens with sp2? In case of sp2, similarly the carbon from its ground state promotes itself to excited state. So you have these things. Now when they are going to mix to form the new set of hybrid orbitals, now in case of sp2, 1s and 2p orbital will mix, the other will not mix. So you can think about it. If you have s and 3p, you sp2 means you have this s and 2p, so it will call sp2. So the last one will remain unhybridized, that is, it is not going to participate in this mixing process. Now you can ask me, is it necessary for S to mix with Px and Py, or it will mix with Px and Pz? It is not that. As I told you, we have named it in such a way, but there you can change the name also. You can give Pz, Py, Px, or Px, Pz, Py, etc. So it is not, because S is spherical in shape. It is not any directional preference. So it can mix any of the two orbitals of P, that is Px plus Py, or Py plus Pz. The important thing is the resultant hybrid orbitals and this unhybridized electron. What will happen to this? Through this mixing, the resultant orbital will be an sp2 hybrid orbital, and the shape of this orbital will be a trigonal planar. So this is a plane. You can imagine a plane of a paper and two corners. So sp2 orbitals means there are three hybrid set of orbitals. Two such orbitals will be projected towards corner, and the other will be other side, so that the bond angles will be 120 degree. This is linear in shape, and this is called